Thank you all for joining our weekly Applied PDE seminar at the University of Washington, but watchable from far, far away. Today, it is my distinct pleasure to introduce Professor Jens Rademacher, who is currently at the University of Bremen. Professor Rademacher got his PhD in the beginning of this century at the University of Minnesota. And then after a postdoctoral stint at Simon Fraser University and actually, I guess at PIMS, right? At Simon Fraser University, and then also at in Amsterdam. He's been at the University of Bremen since. And today he will talk to us about pulse replication and the accumulation of eigenvalues. Thank you, Jens.
Yeah, thank you, Bernard, and thanks, George, for the invitation and the opportunity to speak here. It's great to reach out to the world, into the far, far distance, ever further than before. So it's my great pleasure to talk about joint work with Bjorn Sandstede and Paul Carter. The title was already mentioned. It's about pulse replication and accumulation of eigenvalues. And while the theory is, we believe, a little bit more broadly applicable, the guiding example that I'm going to take here is the FitzHugh-Nagumo system in this form here, and its pulse solutions. So you see, I hope my mouse pointer still, the FitzHugh-Nagumo model will be here posed on the real line. And it consists of these two differential equations. The first one is actually also diffusing and has this nonlinear part f, which is a cubic, as written down here with the 3 zeros. And then it's linearly coupled to this ODE here for w, which entails this small parameter delta. So the smallness induces a slow-fast structure, which is going to be relevant for our purposes here. And the solution that it gives this the name pulse is depicted here, just a sketch. It moves to the left with a constant speed c and has this traveling waveform as depicted here. And its existence has been studied a long time ago. I'm just mentioning a few names here: Carpenter, Hastings, Jones, Coppell, and Lange. And this will be kind of one of the starting points. We're going to modify this a bit, but let me first talk a little bit about the slow-fast structure here. So in the traveling wave ODE, the PDE is going to change. First of all, I get these advection terms with a velocity. And now traveling waves would be where the left-hand side vanishes. And as you can see here on the right-hand side, I still have the differential equation parts, which gives us a three-dimensional ODE, the so-called traveling wave ODE. And what I've done also is that I replace delta by epsilon, which are linked by this velocity parameter c. That's going to be convenient to do it that way. And from now on, epsilon is going to be the smallness parameter. And it is, again, there's this multiplicative factor in this ODE down here. The reduced fast system, as it's called, is obtained by just setting epsilon to 0. And then we basically just lose this last equation and have the system of u and v, where w enters as a parameter. And the solutions of that ODE can be found in the profile as these fast parts here. Of course, perturbed from it, because here we are in the epsilon equal to 0 limit, whereas the picture is for positive epsilon. Now, the other part in the slow-fast business is the slow system, which is obtained by rescaling time. As usual, one gets on the left-hand side now the epsilon factor for the equations without epsilon, and has a new time variable, which I just denote here with a prime. Now, setting epsilon to 0 gives us the reduced slow system, and that consists, first of all, of v equal to 0, which means we can drop v from the second equation. And the second equation now gives such a nonlinear constraint, a relation between u and w, where w is this remaining ODE variable, and that is this slow system as a whole. And it can be found also in the profile, or its solutions make part of it, namely the slow recovery here. And there's also a slow part here in this part. So that's just to set the scene with the slow fast bits, which are going to play a role later on. But as I already said, I'm actually not going to look in this classical parameter regime, which is occurring when A is sufficiently large. There's a certain threshold value, A0 of delta. And when A is less than that value, one actually obtains oscillatory tails. And this is the regime in which I'm looking now. This has also been studied already regarding existence by Hastings in the 80s, and probably a lot more, but let me refer to this recent work by Paul Carter and Bjorn Sandstede, my co-authors in this work, because this was then giving the starting point for the current study. By the way, if there are any questions, you can interrupt me at any time, and otherwise I'll just move on. So in this parameter regime, let me show you a simulation here on the left. Most of these simulation pictures have been done by Paul, so let me acknowledge that. And now the time is running. You see the original profile, and you see hopefully that there is this growth in the wake of the primary pulse, which leads to a second pulse. And then there's a little bit of a sorting stage. And then a moment later, there's going to be yet another of those large pulses growing until the domain is filled. And this is more easily visible perhaps in the space-time plot here on the right, with space horizontal, time is going up. And this yellow line here, that is this primary pulse, which is leftmost in the simulation. And then there are these other yellow lines coming up, which are the other pulses that emerge in the simulation run. And this is actually happening along another line here with a certain speed. Well, and this type of phenomenon was the origin of our discussions, because I had seen things like this when studying my thesis, and never really got around to, and never really got a handle on its analytic properties. So I wanted to get back to this. And then the way towards trying to understand this phenomenon, we found what I'm actually going to talk about. But nevertheless, it is coming from this perspective. And what you've just seen is this temporal pulse replication, which also made it into the title. And what I'm talking about now is the accompanying parametric replication, which is depicted here on the left, where A is this horizontal axis, that's this primary parameter that we are looking at. And the vertical axis is the L2 norm. So roughly speaking, the temporal transition or replication means that we are moving up in the L2 norm because we are adding more and more of these pulses. And that's also in parameter space occurring roughly where this red line here is. And what also happens in this parameter space is that there exist traveling pulses. Of course, that was the original starting point, that here, down here, there's this point, it's going to be shown later more, corresponds to a one pulse, to a pulse that we've just seen. Now, if one does a continuation of that pulse, by this numerical continuation, we find that there's a branch which moves, or which is going in this direction, it oscillates, and then there's a very fast transition, a so-called canard transition actually, and then it folds back down here. And when it ends here, this is actually where we are basically looking as if we were cutting the space-time plot around here. So where there are two pulses, like a bound state of two very close nearby peaks. And as it happens, there's yet another of those two pulses just nearby in this plot, which is on a different branch and connects to a 3-pulse. And then there's a 3-pulse which connects to 4-pulse and so on. There's a whole stack of these, it seems. This has actually not been proven to my knowledge rigorously for this case here, but it appears that with the methods of Bjorn and Paul, this would be possible, because the remarkable result that Bjorn and Paul reached were to prove rigorously the existence of this green branch here. And that is remarkable because this is a branch that stretches in order 1 distance in space, actually, in particular this whole transition here. Strictly speaking, this was proven for sufficiently small epsilon, where this is due to such a canard transition. I won't talk much about it, but I wanted to acknowledge this result because it gives the backbone of the theory I'm going to present here. And this is then the so-called parametric transition. Now, that was not discovered here. This is something which occurs in various models and has to do with the CU transitions that people might have heard of. In particular, it also is known to be accompanied by this temporal transition for a few models, in particular a modified Klaus-Meyer model for vegetation, and in fact also the originator model, which is a extended model related to FitzHugh-Nagumo, but has one more species, and it's a model for nerve impulses. And that is incidentally what I've studied in my thesis, partially at least, where I observed this phenomenon, but gave it a different name. Nowadays we call this pulse adding. Okay, these are the two types of replication that we see here. And when looking at such a parametric replication along a branch, a natural question is, what about the stability of these pulses? Because if it so happens that the temporal dynamics reflects what these branches look like, there should be some stability information that kind of is associated with it. And that's what we started out with, thinking, okay, I mean, we have this branch and that behaves like a center manifold, and then we just show that one can drift along this branch, and that's it. Now, this branch also has this snaking type structure. Here it's a little bit small. I'm going to make it a little bit bigger in a moment, namely here for epsilon 0.02. Kind of oscillates around. So when having this homoclinic snaking in the back of your mind, which people might have heard of, you would think that, okay, there's one eigenvalue which moves through the origin when passing through the folds, and then it moves back. But as the numbers here already indicate, that's in fact not what happens in this case. And we were very surprised about that initially. And nowadays we understand where it comes from. And that is actually the main part of my story. Where do these eigenvalues come from? But let me guide you through this figure a bit more. So on the bottom here, the 0 indicates that there's no unstable eigenvalues. I'll show those in a moment. And here is the plot of the profile, the single pulse that is stable. In fact, the stability of that has been proven rigorously, again, by Paul, Bjorn, and another co-author, Bjorn Sandstede, a few years ago. Strictly not speaking, not in this regime, a little bit further away, but nevertheless, there's good evidence that this is stable, rigorously even. And then halfway up this transitioning, the second pulse has grown a little bit, but not quite to its full extent yet. And that is shown in this figure here. And now we come to these eigenvalues. And as I said, the numbers give the unstable eigenvalues. First of all, at the bottom here, there's 0. Nevertheless, there's all these blue eigenvalues. Let me guide you to the eye. So here's 0 real part. So here is the origin in the complex plane. Of course, the origin is a eigenvalue, but in this computation, it has been factored out, so it's not visible. What is instead visible is all this blue stuff here, which is associated with the essential spectrum of the background state, and it's stable. So here this is stable. This halfway up transitional pulse is unstable, as I already said, and this is shown by these 3 red circles here, which give 3 real unstable eigenvalues, and the rest is again essential spectrum. Okay, so it's a bit more complicated in this transition because there are more than just one eigenvalue going with it, which also shows that, for instance, this transitional pulse has a 3-dimensional unstable manifold, and then a few more things are possible than just one type of dynamics. So which makes it a little bit more complicated to identify what happens in this temporal transitioning. Let us first try to understand a bit better the dependence on this epsilon. So what I'm next doing is I'll decrease the epsilon. In fact, I take half the value. So from 0.02, I'm going to 0.01. Let's see what happens. So the branch has become a lot more vertical and a lot more wiggly. In fact, twice as wiggly. So as the numbers here already show, there's going to be 6 unstable eigenvalues now coming from 6 fold points. And here's the figure of the profiles. Same thing down here, the 1 pulse, it's stable. And this transitional pulse halfway up is unstable now with 6 unstable eigenvalues, twice as many when epsilon is half. And we'll show that there's actually a scaling law behind this. So to give away the kind of key message already, let me formulate now informally this theorem, and the pieces of it will become clear hopefully throughout the talk. So the statement for the accumulation for FitzHugh-Nagumo that we were able to prove is the following. These transitional pulses along this branch, which goes from 1 to 2 pulse, have a certain set, which is an interval here from 0 to a maximum number lambda max of S. And this is the accumulation set of eigenvalues, and there are order 1 over epsilon, many of them. So which means that if you take a point in this interval, then in any neighborhood, as epsilon goes to 0, you'll find order 1 over epsilon eigenvalues. Now there's this funny name here in the beginning. I'll explain this a bit more later, but I can already say in words what it is. That's what we call the real slow absolute spectrum. I'll explain this in more detail. What this M0 here means is that it has to do with the slow manifold that the pulse is traversing. Now, there's a little bit more to be said about this interval. It starts at 0, it ends at this lambda max of S, and this value lambda max of S is actually something we can identify rather precisely. It lies in the interval from 0 to 5/24 as it happens, and it has a very specific formula. In particular, it means that the extent of this interval is order 1 with respect to the parameters, despite the fact that we are doing anything in an order epsilon by perturbation here. The other aspect is that the number of eigenvalues not only grows when epsilon goes to 0, but it also grows or decays along the branch if we fix epsilon sufficiently small. I'll try to explain it by this cartoon picture down here. The horizontal axis is the real axis where these eigenvalues lie. And this value here, 5/24, this is this maximum extent of this lambda of S and the maximum extent of this interval. The green line shows the endpoint, this lambda max of S, and S again in the vertical direction corresponds to going along the branch. So it's basically the same as the L2 norm in the previous figures, from 1 pulse to this 2 pulse. And these circles here, they indicate the accumulation of eigenvalues. So if I take this fixed S value here, or let's say this one here, because there's a number, if I fix this S value here and I consider epsilon going to 0, then they're going to accumulate eigenvalues on this interval here. And that's the only set where eigenvalues accumulate for FitzHugh-Nagumo. That's the one point. And the other point is that if I take epsilon sufficiently small and then move up in S, then I will also see a number of eigenvalues in this interval, but finitely many. And as I move totally up, this number goes down to 2, actually. I should maybe mention that on this vertical axis here, so for lambda equal to 0, there's always an eigenvalue again because of the translation. Okay, so this is the main result regarding FitzHugh-Nagumo with all the details for this specific case. And the abstract theorem, which is behind it, which maybe is the more interesting aspect of all of this, is this one here, which says that if we take an abstract traveling wave family, parameterized by the smallest parameter epsilon, and epsilon lies in some interval, and M0 is the slow manifold associated with this family, then we can identify accumulation points of spectra of the linearization in these traveling waves as follows. Here's again this funny name, this slow absolute spectrum of M0. So first of all, it's only real. That's what this here shows. And then it is the union along the slow manifold of certain sets sigma abs of U0. And I'll try to explain what this is. These are, in words, the absolute spectra associated with these points on the slow manifold. So this set here is an accumulation set of, again, order 1/epsilon eigenvalues for the linearization in U epsilon as epsilon goes to 0 for certain open conditions. Now, this is a little bit weaker than before because here I only say that it is in eigenvalue, in accumulation set. It's potentially there might be more. And one of the candidates for other eigenvalues is actually the complex parts of this absolute spectrum. However, we have not gone over all the technicalities to show that, and it's actually unclear to us whether that's true or not. So we've left out this aspect out of this work. In fact, the complement of the real absolute spectrum in the complex plane doesn't really occur in these cases, it appears. So there's no natural example that we know of, but that doesn't rule it out. And maybe as an additional statement about this, it makes certain connections maybe to people, to things you know, that these accumulations are associated, or the ordering of the eigenvalues are associated with oscillations of the eigenfunctions, similar to Sturm-Liouville theory. Okay, so that's the goal of this talk. I try to explain some bits and pieces of these results, and particularly a specific one for FitzHugh-Nagumo. Okay, so here we go. Once more, this overview. Abstractly, on the left, these two types of transition I've talked about with the branch connecting from the 1 to the 2 pulse. And on the right, the associated picture of these eigenvalues and the accumulations. And here again, shown for the FitzHugh-Nagumo case, where this moves to the unstable half plane and then back through the origin. And these results explain the origins of these point spectra and the accumulation. They provide criteria then also for stability and instability of this set or these sets. And in particular, this suggests rich dynamics near the replication. So as I said, the original goal was to understand better the temporal dynamics of the PDE and the replication. But this has turned out, because of this result, to be a bit more complicated. Let me indicate just one phenomenon that we could identify by numerical simulations associated with it. There's more going on. So on the left, you see again this picture I've shown with the trace firing or the pulse adding phenomenon. That's for a parameter value A, which is here minus 0.0295. And if I take instead A minus 0.0325, so a little bit smaller, then the phenomenon is actually different. And whenever there's one pulse born in the wake, it actually shoots out another one in the opposite direction. That's how to interpret this picture here. So there's indeed a bit more going on. All right, so in order to get a little bit of background for these results, let me spend a few minutes on what most people probably know in this audience, as I've seen you, namely on traveling wave spectra. But nevertheless, I'll hopefully it's not boring for you and just puts the correct background here. So we look at abstract reaction diffusion systems with constant coefficients, diffusion matrix, nonlinearity, and some n number dimensions. Then we get the traveling wave ODE as usual, which is in this first order form, an ODE in this dimension n plus the dimension of the range of the diffusion matrix. The homoclinics of that ODE correspond to pulses in the PDE, periodic orbits to wave trains, heteroclinics to fronts, etc. And the key element in this analysis is going to be this eigenvalue problem here. Lambda v is LV for this operator script L, which is defined by linearizing in the traveling wave, where the first part is just the same as before. The nonlinearity is linearized in the traveling wave. And we cast this as a first order system in space with eigenvalue parameter and just write this abstractly in this form. It is a non-autonomous spatial ODE with eigenvalue parameter lambda. And then the point and essential spectra can be distinguished. First of all, it's well known that the spectrum is characterized by bounded solutions of that ODE, and we distinguish point spectrum where the operator L minus lambda is ferromagnetic 0 and has a kernel, which can be associated with the roots of an Evans function. And the essential spectrum, which is a complement of that point spectrum in the spectrum for these types of problems, which is characterized by a dispersion relation in the asymptotic states. And there one gets an additional wave number parameter and solves a dispersion relation, abstractly written here as d of lambda ik equal to 0. And now the thing is that the eigenvalue accumulation that I will talk about are, of course, roots of the Evans function. But in order to understand where this comes from, we link this to a certain dispersion relation. So it's useful to talk about dispersion relation. And here for the constant coefficient problem, for the asymptotic states, we can Fourier transform directly and get this matrix operator in multiplication operator in Fourier space. And then its spectrum is just given by the zeros of the determinant of that matrix operator, pointwise, for each Fourier wave number k. So there should be equal 0, I guess, for the actual relation. The basic example, which even though it's trivial, I think it's useful to keep it along, right? I just take this scalar Sturm-Liouville operator eigenvalue problem, and then the Fourier transform gives, of course, this relation where the derivatives become these multiplications, and then the spectrum is the sideways parabola when C is non-zero. Right, and now we have to look at what happens on a bounded domain. As it turns out, then the situation, of course, changes somewhat. We replace the Fourier transform by the characteristic equation, and that gives us, instead of the purely imaginary Fourier wave number, a complex number nu here. Then we look at solutions of that relation, which gives the so-called spatial eigenvalues, nu j, as I denote them from now on, which are viewed here as functions of lambda, and associated eigenvectors, which then give a solution basis, and then a temporal eigenvalue lambda is occurring if, or lambda is a temporal eigenvalue if for this particular lambda a superposition satisfies the boundary conditions. So that's just in a nutshell this theory, and then the dispersion relation, of course, for the basic example is just trivially modified. But let's nevertheless look at solutions of that for a particular example, namely, first of all, the periodic boundary condition case, which is well known. And all that happens is that we just discretize the Fourier wave numbers we have available to the resonant ones, and then we have these red dots just lying on the essential spectrum, and in Hausdorff distance, as L goes to infinity, this periodic spectrum converges to the essential spectrum. Now, for Neumann boundary conditions, the situation is different. Now we have a regular Sturm-Liouville problem, so the spectrum is going to be real. And one can check that it's actually this set here, a minus c squared over 4 minus pi times n over L squared, where n is a natural, n is a full number, an integer. And yeah, this is what I just sketch here. We are going to get eigenvalues that lie on such a point set here, which has an endpoint at a minus c squared over 4. And the accumulation at the endpoint is quadratic, but elsewhere it is of order n. So that already indicates accumulations. Both of them, of course, give accumulations. Here it is slightly different. And the accumulation set in this case is in fact the associated absolute spectrum in this case. So here we already can identify this absolute spectrum I've mentioned before. Now, more generally, this also works. The difficulty is to characterize this accumulation set. So if we just take the absolute spectrum as the accumulation set of eigenvalues, we can characterize it as follows. We look at the characteristic equation for the more general problem with any number of components, as here, and for some linearization, again, constant coefficients. We get these spatial eigenvalues. And for simplicity, I just now assume that D is invertible for the moment, and I have 2n of those. Otherwise, it's lesser. And the statement is that for regular D, for such an invertible diffusion matrix and certain conditions, which I won't specify, it's just an open set of conditions, lambda is in the absolute spectrum if and only if the set of real parts of these spatial eigenvalues cannot be evenly split. In other words, for any number lambda, for any number eta, I'm sorry, the number of eigenvalues with real part bigger than this eta is not n. So it's like there's an obstruction to splitting. And that's most easily seen in the complex plane picture here. So these two are for n equal to 2. Now in the first example, I can just take eta equal to 0. And then I have that the number of real parts that are bigger than this eta is 2. So this point is not going to lie in the absolute spectrum. On the other hand, for this example down here, wherever I choose eta, if I choose it to the left of this complex conjugate pair, the number of real parts that are bigger is 3. If I put it on the other side or on top in this definition, it's going to be 1. So nowhere can I split it. The splitting is obstructed, and that indicates that this lambda is in the absolute spectrum. And that goes back to results by Sandstede and Scheele in 2000 for these operator examples. So now I want to link this to the problem of FitzHugh-Nagumo and this replication in the parametric sense. Whereas the origin of the point spectrum is accumulation, well, we can guess now that probably has to do with some sort of absolute spectrum. And then from that, we can also get criteria for stability or instability. Okay, in order to link this, we have to make one leap of thought, first of all. And make the following analogy. So here I plot the profile of this pulse again, zoomed out a little bit, or in rather, where this here is the fast transition, then there's a slow part, there's a fast transition again, that is depicted in here. And then there's in particular this very long slow part. This is going to be the decisive slow part of this profile before there's a transition back somehow to the background state. And the analogy I want to make is that I want to view the points here as equilibrium, and rather at the first idea, take all of these together to be one equilibrium point. And then we actually have a profile which looks like this. There's this initial peak. Then there's a long plateau where the profile spends a lot of spatial time near another equilibrium state, noted by P here, and then it transitions down. And in the limit, when L goes to infinity, this profile actually converges to a heteroclinic cycle, in the sense that when L is infinite, we have the one heteroclinic connection from the background state to P, and then we have the other heteroclinic connection from P to the background state. And this scenario has actually been analyzed in the vicinity, so to speak, of these previous results. And it turns out that eigenvalues accumulate as L goes to infinity, again on the absolute spectrum, with a little constraint, namely on a certain most unstable part. I won't specify in any more detail, but certainly one can identify exactly where that is. And it has to do with the absolute spectrum of this plateau state, P. Now, coming back to this problem here, we actually don't have equilibrium points, but we do have a slow drift. So it's like moving through equilibrium points slowly. And from that viewpoint, the goal is now to extend this theory to the case of a slowly varying P. So this plateau state is no longer fixed, but it's going to be slowly varying. Oh, I'm very sorry. This should be epsilon x, not epsilon t. I've overlooked this when changing. This is slow in time, in space, in spatial time. Okay, so let's see how this works. I mean, we've already seen Sturm-Liouville type operators with constant coefficients. What happens if we now take slowly varying coefficients, and how do we get information about the eigenvalues in that case? So for that, I'm going to look at this prototypical example here, just a second order differential equation with a multiplication operator lambda here, just a multiplication. And this capital lambda is slowly depending on x and on the eigenvalue parameter. And more specifically, just to show some flexibility here, I'm looking at this form with a constant lambda 0 that just moves the spectrum, then the eigenvalue parameter itself, and then this slow drift, which goes with speed capital lambda 1. Right, so it moves down in a way when psi, which is the slow variable epsilon x, varies over the interval. And here I'm looking at linear boundary condition spaces, say Neumann or Dirichlet for simplicity, in the UUX plane and on the interval between 0 and 1, just to fix the thought here. So psi moves between 0 and 1, and x moves between 0 and 1 over epsilon. Then it turns out, and I'll explain how, that the slow absolute spectrum we get is a semi-infinite interval again, like in the previous Sturm-Liouville example, where the right endpoint is not surprisingly related to lambda 0, because as I said, lambda 0 will just shift the spectrum, and also includes here this lambda 1. Lambda 1 now with the coefficient that we don't see here, it's 1, which comes from the fact that it's the most unstable when psi is equal to 1. How does this come about? Well, let's just fix a position psi. So pretend it would be an equilibrium point. Let's look at the spatial eigenvalues that come out of that. They solve nu squared is this lambda function. And that gives, of course, just these square roots. And now remember the obstruction to the splitting for the absolute spectrum, and that occurs in this case precisely when this discriminant is negative. Right? And when is this discriminant negative? Well, that is exactly the case when lambda is in this set where lambda 1 is replaced by lambda 1 times psi. But now xi, of course, varies between 0 and 1. So the largest one is just lambda 1 itself in this setting. Or in other words, lambda is in the slow absolute spectrum if and only if there exists a xi 0 in this interval 0 to 1, such that the spatial eigenvalue pair nu plus minus of xi 0 is purely imaginary and of the form I times omega xi 0 with some frequency parameter, omega, or frequency, omega of xi 0. Well, and this shouldn't be in R, but in IR, I'm sorry. Okay, so how does this now relate to accumulation of eigenvalues, this preparation, right? So far, I've just explained how the definition of the absolute spectrum fits. And first, I want to give you a heuristic explanation how it works. Here's just again the setting, and I'm choosing now a lambda which is less than minus lambda 0. Why do I do that? That's because in this case, I'm going to get oscillations for all xi in 0 to 1, not only for some xi, right? Because xi equal to 0 is then removing this part here, and this discriminant is still negative under the condition that lambda is less than minus lambda 0. In that case, more specifically, I get oscillations with this local frequency omega of xi and lambda given by just the square root with the negative discriminant. Here, and this is some positive number which is bounded below by omega 0. Now, geometrically, what happens now is that I want to transport the left boundary condition at xi equal to 0 to the right boundary condition at xi equal to 1, or x equal to 1 over epsilon, while this is just rotating all the time with at least frequency omega 0. And now, intuitively, it kind of makes sense that because of all these oscillations that happen, it should not be too hard to hit the boundary condition. So to fulfill the boundary condition, thereby generate an eigenvalue. And more specifically, and I'll explain more in a moment, one can state it like this. The condition that one actually needs is that these frequencies vary regularly with lambda. Right, so suppose that we are at a lambda 0 where we might not have a closed setup here, so the boundary conditions are not met. Then we would like to perturb in such a way that they are met. And we want to meet them actually many times. And when omega is regular in lambda, it turns out that we actually get order 1 over epsilon nearby lambda that meet the boundary conditions, and thereby order 1 over epsilon eigenvalues. As I said, this was more the heuristic viewpoint, but it gives a geometric intuition, I hope. Let's be a little bit more rigorous and sketch a proof here. So one approach is to just look at the angular ODE in the UUX plane, which, believe me or not, can be written like this. So theta is the angle, theta x is minus omega of epsilon x, this frequency I just talked about. I've omitted here the lambda dependence, plus an order epsilon perturbation. And what we want to understand is how often this passes through rounds of pi. Let's, for simplicity, also take just the same boundary conditions left and right, so that we always need to get, we meet them when we move 180 degrees. And then the decisive quantity, or natural quantity, I should say, to look at is this rescaled phase jump, which says, okay, I'm looking at the difference between the angle at 0 and the angle at 1 over epsilon. Right, this is how far the angle has moved, and I'll rescale this for reasons that become apparent in a moment with a factor epsilon. Because if I do that, then I can just rewrite this as epsilon times the integral from 1 over epsilon with omega. Okay, so here I've sneaked in this lambda dependence again, plus order epsilon. And then I can rescale in the first integral and just get this epsilon independent as the integral over these frequencies with variable xi plus order epsilon. Okay, so this is just the observation. And how does the phase jump relate to eigenvalues? Well, as I said, whenever we move around by 180 degrees, we meet the eigenvalue, we meet the boundary conditions again. So that means that this phase jump lambda should be in this set here. Epsilon k pi, where k is an integer. So this is a uniformly dense set with distance uniformly epsilon. And we want to hit points in that set. by modifying lambda. So under what conditions can we expect to be able to create solutions? Well, the simplest one, implicit function theorem, would be if the derivative of this capital delta with respect to lambda is non-zero at some point. Then we are guaranteed that locally it's linear and we will meet 1 over epsilon points of this set by variation. Now, the only observation that's missing is that this derivative of lambda with respect, capital delta, sorry, with respect to lambda is actually turning in this integral to the derivative of the frequency omega with respect to lambda. And having that this frequency is nowhere zero, we are guaranteed that the derivative of this delta is non-zero. And then we can close the argument. Right, so for this particular example, it's straightforward to complete the proof. And this gives already the key ideas for the FitzHugh-Nagumo situation. And now I'll try to link this to the FitzHugh-Nagumo. Remember that we had this slow-fast structure with a spatial ODE. And as I already said several times, key is the slow part. Well, there are several slow parts. And these slow parts form such plateau states for this idea of heteroclinic cycle. And the only part that is actually relevant turns out to be this one here in the wake of the primary one. And the reason is that everywhere else, the absolute spectrum is going to be stable anyway. And another reason is that this condition, which appeared on the most unstable part of the absolute spectrum, this also rules out certain parts of this profile here. So we can focus on this here, which comes from the slow manifold. And let me guide you maybe through this picture, first of all. So the red curve is the slow manifold from this cubic relation. F is cubic, remember? The black curve is the profile of this pulse that is shown on the right. It comes from the equilibrium. It makes a fast jump to the right, to this branch. Then it traverses along this slow manifold. Then it makes a fast jump back to the other branch of the slow manifold. Then it goes here. And then it actually, that's not easy to see, but then it kind of follows this unstable, this middle branch of the unstable manifold, of the slow manifold, a certain amount of spatial time. Here it goes roughly, say, up to here. And then it makes yet another jump again to the slow manifold before oscillating into the equilibrium state. Sorry, my kids. This is very disturbing that there's a sound in the background. Well, apparently not. Okay. So here we go with the slow branch in the center. As I already said, this is the key one. And I also already said that this is the unstable one. And the fact that this is unstable generates the aforementioned canard phenomenon, because trajectories are very sensitive when you want them to pass along an unstable slow manifold. Now, the link to the absolute spectrum is then as follows. We view the points on the centerpiece of the slow manifold as equilibria and ask what is for this FitzHugh-Nagumo setting the condition for the absolute spectrum. Well, we have to look at these spatial eigenvalues. And in this case, the obstruction to splitting is given by the fact that the real parts of the eigenvalues with the two largest real parts coincide. And in pictures, this is shown here. We have these three eigenvalues which are separated. Then clearly this is not in the absolute spectrum because I can split. The most unstable ones are not having the same real part. On the other hand, in this picture here, the two eigenvalues with the largest real parts have the same, and I cannot split. This is the obstruction condition in FitzHugh-Nagumo, and that point is going to be in the absolute spectrum. And it turns out when one computes this, that this piece is a little circle here. It's hard to see, but on the entire center branch up to this circle, this is where this condition is satisfied. So everywhere here, lambda equal to 0 is going to be in the absolute spectrum. Lambda equal to 0, more specifically, then it looks roughly like this here. The fact that this is in the absolute spectrum then shows that the absolute spectrum is actually going to be unstable. And the reason is that this difference in imaginary parts is robust if we change the real part of lambda. So by changing the real part of lambda a little bit, the complex conjugate pair nu of lambda is going to stay complex conjugate. And this obstruction is still happening when moving in particular lambda into positive reals. So it's going to be unstable, this absolute spectrum. Well, with this, we come back to the theorem statement, namely, just to recap, I had this before. We had introduced this slow absolute spectrum that depends on the slow manifold in an abstract way. And in this particular example, it turns out it is this interval I've tried to indicate just before, where 0 lies in the absolute spectrum, and then perturbing from it also lies in the absolute spectrum. Of course, perturbing to the negatives would also lie in the absolute spectrum, but this part is going to be cut away due to this condition that only the most unstable spectrum is relevant. And in this case, this is actually the only set where this happens. So it is actually the accumulation set. And one can now compute what I said before, that this maximum part of lambda lies in this interval, and this funny value 5/24 occurs. And then we have this picture, as I said before, if I fix a value of S along the branch, I'm actually fixing basically this takeoff point here, where the black trajectory is moving away from the slow manifold. And when S is moving down, I'm going to zip this open, so to speak. And if S is moving up, I'm zipping it more closed. And halfway up, the S is going to be here, roughly speaking. And then when S is going all the way up, I'm going to unpeel it again and go down. But this being said, it's not so relevant. I hope the key message came across that whenever the trajectory spends significant amount of spatial time near this center part, then this is going to generate eigenvalues because of this eigenvalue structure and because of this link with the absolute spectrum. In order to make all of this rigorous for FitzHugh-Nagumo, there's actually quite a few details to be done. So it's rather technical and extensive. One needs to talk a lot about exponential trichotomies and so on, because one wants to link this, of course, as I said before, actually to the Evans function, which counts eigenvalues and so on. But I'll skip all this for tonight. Actually, here it's 10 to 9 in the evening, so it's a good time to be a bit more on the relaxed side. Let me just close with a few more comments on the additional complications that come about. So in FitzHugh-Nagumo, the situation is a little bit more complicated. And I'll try to explain it by coming back to this prototype. The prototype that was a second order equation with slowly varying coefficients. And if this would be as I explained there, then the scenario in FitzHugh-Nagumo would look like this. I have a fast jump from the background state. The background state is non-obstructed, so it is doesn't have spectrum in the absolute relevant absolute spectrum, at least. Fast jump to the slow manifold. On the slow manifold, immediately I have this absolute spectrum configuration, and I'll drift everywhere with a uniform oscillation frequency, and then I'll jump back. And if this were the case, that's actually relatively easy to control. And one can show that this uniform oscillation is going to generate uniformly eigenvalues. However, in FitzHugh-Nagumo, it's a little bit different because when this fast fiber jumps to the slow manifold here, I'm actually not at a point on the slow manifold where the absolute spectrum condition is fulfilled, but rather it is hyperbolic. It's like this. So I have real eigenvalues. And only when I drift along the slow manifold sufficiently far, there's going to be a transition where these two eigenvalues join and move into the complex plane. And then I have this configuration that I mentioned with the absolute spectrum. And then I'm going to drift out again also through such a transition. And we call these transitions Airy transitions for a reason which will become apparent in a moment. It has to do with Bernoulli-Koptevani type transition, if you will. But here, the key thing is that spatial eigenvalues meet and become complex conjugate, not necessarily with zero real parts. So that is actually the scenario that happens in FitzHugh-Nagumo, and that gives a lot of headache if you want to prove details. And I'll just point out what happens in this basic prototypical example by augmenting it in this direction or pointing out what to do. So here's again the second order operator equation with this eigenvalue parameter as before. And what I did before was taking lambda strictly less than minus capital lambda 0, because that guaranteed uniform oscillations. Now I'm taking lambda in the opposite direction, namely bigger than this minus lambda 0, but still less than lambda 1 minus lambda 0. In that situation, there are actually no oscillations, because the eigenvalues will be real when lambda, when psi is small. Then there is a certain point when these eigenvalues become double and move into the complex plane. That's this Airy point, and there's an Airy transition to oscillations. And in pictures, it looks like this. At psi equal to 0, the spatial dynamics is hyperbolic. Right? There's no oscillation, it just moves according to the stable and unstable spaces until psi a. And after that, the oscillations set on and become uniform. So, and then I have this scenario as before, basically. And the difficulty is to control what happens with the boundary condition space on its way into this oscillatory region uniformly. And turned out to be actually more complicated than we initially thought. So we had to extend the paper a bit by proper rescalings and so on. In this particular example, it's not necessary to do all that, but for the complete result, it is rather delicate. But with a little bit more effort, one gets the same type of result. Whenever this derivative of these frequencies is non-zero, now beyond the Airy point, then we get order 1 over epsilon eigenvalues in the vicinity of any point in this slow absolute spectrum, and therefore order 1 over epsilon eigenvalues. Okay, so now I'm done. Thank you very much for your attention. And here's the preprint. Actually, I just realized today that I should update the archive version as well. Still some errors in it.